for you. Hi,
All
everybody.
right. Yeah, hi everyone. It's 11 a.m. Eastern Standard Time, so we are about to start. This is the first of the Module 8 research presentation. So this is going to be just 1 hour. And then today we have the honor to have Professor Prem Saga. Again, those of you who were here at the beginning, Module 1, Professor Saga gave an excellent presentation in Module 1. So today we have him again for a 1 hour presentation. So the topic is application of data science in COVID-19 and also data mining in higher education. So again, welcome again, and then good day, everyone. Over to you, Professor Trent.
So much, John. Good to see everybody. I hope everybody's doing great. Some of you who were here for Module 1 expressed interest in also doing data mining. So I put together, well, I'm sharing one of the papers that we've submitted that's been accepted to the American Marketing Association as a competitive paper for finding trends in improving higher education. Right? So how do we make things more effective for students? How do we get them to feel more responsible and help others as well, and improve their academic performance? So we'll see some applications of COVID, right, data science towards COVID, and we'll see some applications of data mining on a higher education data set. So I'll go over a little bit of an overview. And John, do we know how many folks are new from Module 1? Is it hard to say? I see some familiar faces. Yeah. So.
No, yeah, I think most of them, maybe a handful, but most of the audience here started with Module 1, so they know you.
Okay. Good. All right. So then I'll go straight to the COVID data. All right. Let me share my screen. Okay, so everybody should see that. And let's pull up COVID model. Yeah, we can start here. So I'm just going to open up some charts for you all to see, and then I'll explain what it is, how we did it, and what we think is going to happen. All right, so let's see. Okay, so I should be able to pan around here. Let me move this out so you can see it. Okay. All right, so by some miraculous coincidence, today marks the 1-year anniversary of COVID in the United States. I'm certain we didn't set it up this way, but it happens to be the case. And yeah, what a year it's been. So let me talk through what you're looking at and what can be gleaned, and then I'll take you through some aspects of the model. At a high level, we built a COVID-19 model to project death rates, right? So how lethal is it, right? To project deaths and to project infections. And we did that for every country in the world and every state in the United States and every county within the United States. So there's an enormous amount of data. And then after doing all that, we then ran screens to say, okay, you know, there's too much data to look at altogether. Where are the hot spots? Where are things getting better? Where are things getting worse? For the, you know, for death rate, deaths, and then infections. And so that those of you who all know me know that I enjoy having questions. So if you have questions, interrupt me because I'm sure other people are thinking the same thing, right? Okay, so let's talk about deaths in the United States, right? And I'll walk through this chart. So from the very top, what we have is deaths U.S. forecast in 14 days. So we give a 14-day projection and we give a 6-month projection. And the projected deaths are 4,600 and 9,000, right? What's interesting about that is the current is actually more than what we're forecasting, right? So, and I'll talk about, thanks, Stacy, yeah. So I'll talk about why that is the case, right? But our forecast is currently in 4 days, 469,085 deaths. We're already at 529,193. The current velocity is 1,296.321, but really 1,296. And what that is how many deaths you're adding a day, right? So every day we're saying around 1,300 people are dying in the U.S. Okay, and that correlates to this linear trend line over here. You'll see there's a yellow line as well, which is a curve, which is cubic. I'll talk about that in a second, but I'm just walking you through it so that once you see one of the model's outputs, you'll be able to understand it as we move around. Okay, so we have the slope of this line, right? So the amount of deaths per day we're seeing is 1,300. And then the acceleration, which is, okay, yes, you have so many deaths per day, but is it increasing every day, right? And so the good news is, well, it would be good news if it was closer to the projections, that it's not accelerating. At least our leading indicator, which is the blue line, is saying that acceleration is not on the move for deaths, okay? The other thing is there's a possible peak, right? And I will take you through how we do all of this. There'll be drawings and whatnot of how we derive this and how we came about doing this so that you can do similar analysis if you'd like to. So there's a possible peak up here, and so there's two things. We call these turning points, right? So let me see if I can zoom for you. That may be better. So there's a turning point here. All right, this is a couple of months back, right? And there's a turning point here, right? And so this is a turning point on our way up, inflection point, if you will. And this is another turning point saying that things are, in fact, slowing down, right? At least in the short term, we can see that. Right? And I'll talk about how we derive that in a couple of minutes. So there's a possible peak for deaths, okay? And let me step back as well. What you're looking at is the x-axis is time, right? So this is days from the first infection, from the first death, right? So days from the first death, we're now at about 400 some odd days in from the first death. And this timeline starts from the first death ever recorded, which is why it's not 365 here to the day. So the first death ever, and we do that so that you can see how things changed versus other places, right? Everybody has the same time axis. Okay, so time is going left and right here, so the x-axis, and up here in y are cumulative deaths, right? So we're not doing deaths per day because you can get that from the slope of the line or the curve. We're actually showing total deaths over time, right? And a thing to note about that is this chart will never go to zero, right? Because it's cumulative. Whereas deaths per day, let me see if I can annotate here. Right, so, let me make this smaller. Deaths per day will eventually drop, right? But deaths cumulative will not go to zero, but it will flatten out, okay? And you can see we thought things were actually going to stop for deaths back here almost, what is that, 150 and 450, so almost 250 days ago. And it didn't. But you see, we were in lockdown here, right? And had we continued at that trend where things were slowing down, the indication was that we'd be able to actually eradicate deaths by day 186. However, we came out of lockdown, right? Behavior changed, and we continued to run up, and then about 150 days ago, things really took off, and deaths exploded, and now things are starting to taper off. I'm curious from folks in the audience why you think that is. Let's actually talk for a second about that. We'll give it a couple of minutes. Does anybody have ideas as to why in the U.S. Deaths and infections are slowing down? Let's see if I can see my business in here. The jury is still kind of out on it, right? So I can tell you, and I'm just looking over here because I'm sharing this screen. There are two competing thoughts as to why this is the case, right? The first one, and the CDC director actually issued a statement last week about this, but I'll give you the two spins. The first one is it's the vaccines, right? We're vaccinating more people, and so transmission is slowing down, less people are dying. Less people are dying, so transmission is slowing down, so less people are dying. And that is what is the big factor here, right? The second idea is that we had a pretty terrible winter. And it's harder to get together and, well, in travel when the weather was so bad, right? In particular, Texas, Texas got it really bad. And I think it's fascinating that Texas got it so bad, and that Texas is now the first state to say, okay, everybody can do what they want. You don't have to wear masks and whatnot. So data scientists, some would say we're superstitious. I look at coincidences, right? And I always, think about that. Like, how can it be that they got hit so bad and yet they're opening up so quickly, right? Is there a correlation? So it is hard to definitively say, but I can tell you that the CDC warned again that everybody has to wear, continue to wear masks and be vigilant about this, because they're vaccinating about 2 million people a day, right? Which is actually pretty amazing. I still can't get it in neurons, but they're vaccinating about 2 million people a day. Last count I saw was 30 million have been vaccinated. It may be up to 50 million, depending on how you count. If you count, everybody once, or everybody's got it twice. I think everybody who got it once is 50 million, and everybody got it twice is around 25 million. So let's say even 50 million people have been vaccinated, right? There's 350 million people in the U.S., right? So that's like, what is that, like 15% have got it, roughly, let's say. So is that enough to account for the tapering off? Maybe, maybe not. Maybe the combination of that with the bad weather and people not getting together did it. I would like to think it's largely weather, because, that's the big thing that changed, right? So, yeah, the spring break is coming. They're anticipating an increase, right? And the CDC director went on to say, thank you for that, Helena, that they know, and I'll send you the article as well. I'll put a link in the chat. CNN put it out this morning. So they've come out and said that we know that people coming together causes virus transmission, right? And so we can clearly say that people are not going to come together if there's, a natural disaster, right? It's going to be very hard for everybody to come together. So, yeah, let me see. I'm just looking at the chat windows to see anything else that I can glean from what you're saying. Yeah. Okay. So I saw it come up twice. Yeah. Anticipating an increase in COVID. Yeah, and I actually anticipated as well. I'm curious to see what the folks in the room think. And so, yeah, so let's think, and very quickly, if you're vaccinating 2 million people a day, okay, so in a month, that's 60 million roughly, right? And so in 10 months, that's 600 million, right? So we should get there at 60 million, so 5 months. We're 5 months out at full velocity. If you maintain at 2 million a day, you're 5 months out from getting everybody vaccinated, right? Now, the administration has come out and said that they'll have everybody vaccinated, all adults, by the end of May, which is approximately, I think, last we checked, about 200 million people. Yeah. So that does something because adults are more at risk than youth, right? So somewhere between the end of May and, let's see, what is that, 6 months from now? So this is March, September, right? We should have most of the country vaccinated. But then, of course, there is the problem that there are the variants, right? And there are issues with the vaccines being effective against the variants. Moderna has already come out and said that it doesn't work against the South African variant. There's mixed data with Pfizer, and the Johnson & Johnson vaccine is, 85% efficacy, but it's not as good as Moderna and Pfizer, which are stating 95% efficacy. However, it's better against the South African variant, right? So long story short, I think we're going to be wearing masks for a long time. I'm never going to take my mask off until I'm very, very sure about all of this. And I would still be very cautious, right? I personally believe it is weather phenomena, right? But, the data will tell. Okay, let me keep going. So yeah, we say here possible eradication on day 186. Days till eradication minus 227. So we made a call that it could stop if we had continued to be in lockdown. We opened up, it did not. And then what you're looking at over here is the percent difference from probable. Okay, so the blue line is probable. I'll talk about how we got this. I'll show you in detail how this happened. And the yellow line is possible. Okay, and as we see, this will show you the big difference between how models are built for COVID, right? And so what we're saying is the percent difference from probable is 17%, right? So where we are right now, okay, which is the red line, right? These red dots are the actual deaths in the U.S. The difference between this point, right, so 529,193, and the predicted line is 17%, okay? The difference between the possible, which is the yellow dashed line, is minus 6%, so that's a little bit above where the deaths are. And the total difference between probable and possible is 23%. So that represents the spread of where we can be right now, okay? And the blue shaded area represents that spread as well, right? This is the uncertainty that we're facing in the model. So, okay, so that's deaths in the U.S., okay? Now let's look at infections very quickly. So infections has similar phenomena, right? We thought that it could actually stop very early if we had lockdown, but we did not lock down, we opened up. There's a turning point over here where it really exploded. We come up, and there's a turning point now where things slowed down, right? And our current projection is, and this is for infections, we forecast 33 million in 14 days, right? And I remember when it was like 1 million, right? I remember being scared at 10,000. And now we're at 33, well, we're at 29 million right now, which is unbelievable. Okay, so, right, so we're at 33, our forecast is 33 million, we're at 29 million right now, and let me explain this. Okay, so each of these lines has an equation for it, okay? And the first line, which is Y, right? And Y is the most likely fit for the phenomena, right? This is what we believe is most accurate, is given by, 269.5 squared. That's 269.5 times x squared minus etc., right? And so this is quadratic. The possible line is cubic here, right? So we give you the coefficients for as to y, or what is the cubic coefficients for this. And then what happens is we have y prime and y prime prime. Anybody want to take a guess what those are? I'm curious. You can put it in the chat window if you'd like. Yeah. Let me let this. I'll keep this open for 60 seconds to sort of break the ice because I'd like to hear from the audience. So we have these basic lines, right? Y, our best guess for fit, and possible is, the next most likely fit for the phenomena. And then we have y prime and y prime prime. And I'm wondering if anybody can tell me what they think these two are. Where do they come from? You put it in the chat window. If nobody answers in 60 seconds, I'll talk about it, but I want to give you guys a chance to think about this. Let me give a hint. Give a hint, right? There's a comment coming in now. 30 million, 75% of them vaccinated, about 260 people. 262 million, right? Mm-hmm. Okay. Okay. All right. So this y prime and y prime prime are actually the first and second derivatives of the most likely equation, right? And I'll talk about why that's important, but in the beginning, there was so much rhetoric about flatten the curve. And everybody was like, fighting about, is the curve going to flatten, okay? And so now let me do some drawings so that I can explain, what is going on here. Okay, so best way to do that, I'm going to unshare this screen and share a different screen so that you can see some explanations as to why this stuff happens. Okay, so let's stop sharing this. And this will talk about how the model was built and why we chose to do it a certain way as well. So let's do, and I'm watching time. John, I have until noon.
Yes, I believe so.
Okay, thanks, Donna. Okay, let's do. And let's do. Let me do a new page here for you. Okay, this is fine. I'll just pick up from here. You might share this screen. Okay. Let me move this over here. Okay. All right. Can everybody see a large notebook? Yeah. All right. So let's close this. Okay. And I'll talk about now. Make sure this is working too. I may have to do it on the other screen because of this. That works. And that wants to do it on a different screen. All right, I'll do it on the same screen itself. It may not be as neat, but we'll get it. Let me stop this one. Okay. Sometimes the monitors act a little strange on WebEx, so I'm just going to pull it to my primary screen, and I'll sketch it for you there. Okay, so here, WebEx, share, here, okay. All right. Okay, so let's see. So hopefully everybody, okay, yeah, that's good. So, all right. And let's make this green. I'll make this a little bit larger. Okay, so if you have, let's say some data points, all right? All right, and let's say we have something along like this, all right? And you're trying to figure out where is this going to go, right? So this is time. Okay, and let's just say this is depth. All right, you have some options. Okay, the first thing is, and there's some competing technologies for this, right? So the first way to do this is regression. Okay, and there's a variant to that, which is regression with calculus. I'll just write calc. And then, you know, modern techniques for this are neural networks. I'll just write neural net. Okay. And so let's say you choose regression. Okay. So what happens is, okay, now you have to come out and say, all right, you know, we can definitely, you know, fit this with a linear trend line. Sure. Okay. And you could also fit this with, let's say, a quadratic line. Okay. And you could, you know, you can continue to go up in order. And so, first of all, there's a couple ways to fit it, right? But, and let me also add something in here, right? So under A, there's A1. Okay, so let's say A.1, right? And this is polynomial. Okay? And the other way you can do this is, let's say A.2, is choose an equation. And this is where the big difference happens. This is why we were very different from IHME, which I contend is still wrong. Okay? You can go to get data.ai, and I'll put a link in the chat box. And we've talked about why IHME's model was wrong, and I think that was a large reason why we relapsed. Right? That data was used to say that things are much better and we should open, and then obviously things did not get better, and we have all these steps. So, okay, so you have to decide if you're going to choose an equation, because there's many equations you could take, right? And we could have chosen to use a sinusoidal equation, okay? You could have chosen to use A.2.1, something called the Bass equation, okay? And there's formula to show that in epidemiology it's used a lot, that things taper off, right? It forms this sort of logistic curve, okay? And so you could have chosen to fit it to a logistic curve that, hey, it's going to pick up. We know that it's flat in the beginning, then it's going to take off, and then it's going to taper, okay? And the vast majority, including IHME, chose this, right? And that works, and things look very smooth, but the problem with this is you're calling the top. The model is biased towards, oh, it's going to straighten out. Right? And if you look back at the actual data and what's happened, let's look at infections, right? So you're here and it starts to smooth out, and then it takes off again, right? And now we're here. And this was much worse in the case of deaths, right? So we're here, and we've started to smooth out, and then it picked up, and now we've gone up again, right? And so it artificially calls the ball early. And if you look at IHME, I'll leave that. If we get time, I'll come back to it because I definitely want to show you the data mining stuff as well. You'll see that their model is very much, you know, we believe it's going, I'm going to draw in a different color actually. We believe it's going to be something like this. Okay? And that's problematic because you call the ball early. And that's why we thought, oh, there's only going to be 70,000 deaths, okay? And there's only going to be 100,000 deaths, right? And now we're at, you know, what is it, 500 and some odd thousand? Let me get the number correct, actually. So there are, that's infected Texas. Oh, I'm in a different window. Let me pull this up. So we need deaths US, right? So there's currently 529,000 deaths. Okay, so certainly more than the 70,000 that were called before, right? And the rate had picked up, right? This is definitely not logistic, right? This is on the move, and it may turn again. We have to see. So, all right. So we didn't want to do this because we knew that there would be bias if you had picked this, all right? And so what are your options? Well, you could have chosen a number to come in here, a different type of equation, right? But one of the simpler ways to do this is to choose polynomials, right? And what you can do is you can say, let's say that this is order down here for the polynomial, right? And this is going to be the error, right? So what will happen is if you fit at, you know, a zero order polynomial is just a constant. It'll be like 50, okay? And so that's going to be something like, and I'll draw this, that'll be something like this, okay? No slope, it's a constant, all right? So you'll get an error, which is quite high, all right? So this is, and for those of you who are already data scientists or those of you who are aspiring data scientists, this is where the magic happens. This is it, right? Where you draw the line, literally, where you draw the line is all we think about, right? Is it quadratic? Is it linear? How do we support that? All of that comes down to what I'm about to show you, okay? So as you increase the order, all right, the curve is going to get more and more close to the underlying phenomena. This is a fact. This is a function of polynomials. Because what will happen is, you know, as polynomials go up, what's happening is the, you know, a third degree is going to be, you know, let's say a cubed plus b squared, etc. Right? And if you go to say ninth degree, right, this is going to be a to the ninth plus b to the eighth, etc. Right? And these coefficients and to these powers make the curve much more expressive. Okay, and in a saturated setting, you would see a polynomial with the amount of points, right? So let's say we have 50 points, okay? So points equals 50, okay? And if you had a nth term, right, equal to 50, then we would fit every single one of these perfectly. You know, it would look like this. Anybody know what we call this? You may be muted. Yeah. Yeah. So in data science, this is what we call overfitting. Okay? And what it is our model would be 100% correct. We drew this curve that exactly predicted every single one of these points with precision. The problem is it's too specific to the training set, too biased, right? And so where do you draw the line? Here we go. So it turns out that as you increase the order, okay, of the polynomials, you become more and more specific, closer to overfitting, okay? And what will happen is you'll see a diminishing returns curve like this. This right here in data science and engineering is gold. This is it. okay? Anytime you see diminishing returns anywhere, gold. Anybody know why? Diminishing returns are gold because there is an optimal point. I'll give you my favorite example of diminishing returns, okay? Let's do this as sleep, okay? And we'll do productivity, okay? So if you get very little sleep, and I'm assuming no one's on drugs here, okay? Like, this is for normal human beings that are not using like Ambien or whatever, okay? So if you get very little sleep, you'll have, low productivity, okay? And if you get, more sleep, you'll probably have more productivity. Yeah, thank you, John. And so at some point, as you increase the amount of sleep, let's say that this is 8 hours over here, okay? Did that just magically close? Let's say 8 hours here, right? Oh, no, I had it. Okay, that's fine, yeah. So this is 8 hours over here, all right? So at this point, productivity is good. But what happens if you start sleeping for, say, 16 hours? What happens, right? I mean, these are numbers. We have to think about it. Well, you would not be able to get to the office and, say, see your kids, etc., right? So productivity is going to start to drop, right? And, of course, if you slept for 24 hours, productivity is going to be 0, okay? So where do you draw the line? Where do we decide that we're going to sleep, right? It is a diminishing returns type curve, okay? You may look at this, I've drawn this naively, and it looks quadratic, right? Inverse quadratic, but it could be something else, right? But the point is, there is a curve, and this is why Newton and Leibniz obsessed, because they knew if they could find the slope of this point, right, that they would get the equation and the points. They need this slope because they need to get the critical point of inflection here, right? So this is a simple example. We can pick it out. But what if there was an enormous amount of data, and there were many, peaks and valleys, right? So, there we use calculus to find these things, and that is exactly what this is. So for all of us who, I at first did not appreciate calculus, and now all I do is think about calculus. Calculus gives you the inflection points, right? It gives you the maxima and minima of curves, right? And that is critical because calculus here will tell you the slope of the tangent line, stress and performance is similar to the return. Yes, yeah, absolutely. So good point. And so that is exactly right. If you have a little bit of stress, there's some performance. You get too much stress, performance is going to fall off, right? Absolutely right, yeah? And so at this point, the mathematical property is y prime is equal to 0. All right, the derivative of this point, okay, it's flat. There is no slope to this line, okay, is 0. And then we use y prime prime, right, to see the direction of this, right? It's the second derivative test. But the point of this is you have to pick a point where you're going to make decisions and support it. And the way we chose what polynomial we were going to use, because we didn't want to use a set equation because it implies bias, is we looked at this data for the errors, okay? And we found the derivative of this line, okay? And there's actually a way to do that geometrically. If you look at this, right, you can draw a line from the first point to the last point, okay? So now you have, these points out here, and you have a line intersecting from the first point and the last point, okay? And what you can do now is rotate the data, okay? And if you were to rotate this data, all right, this would give you something like this, right? There's that line again, and here's all these points, okay? And then what happens is you have to find the inflection point. Where does it make sense that the error is falling off. But if we keep going, yes, error continues to drop, but it does so at a diminished rate. So much so that you will begin to be too specific, right? Just like we decided that 8 hours was enough for sleep, okay? At this point, we are dropping the error, but you are increasing the chances of being too specific, right? You're running into the chance of overfitting. Okay, so another way to think of it is the best bang for your buck as far as error versus overfitting is right here. Okay, so what do? We find the derivative of this point, and the way you do that, anybody know? So the way you can get that is, this is now, believe it or not, this turns into trigonometry. Okay, you can find so you have to do some axis rotation. Okay, so we do some axis rotation, and then you take the point that is furthest away from this line between the first point and the last point. Right, so you reduce this problem of where do you choose the equations, where do you come up with the ideas for what the fits are going to be, to this math problem of finding the optimal point of error versus overfitting. And this is it. This is how the vast majority of good models, particularly unsupervised models, work.
Fiend.
Right? Yeah. Oh, go ahead.
Hi, baby.
Somebody have a question. I missed it, but if you have a question, you can definitely interrupt me again. So that is how the model is built. And I encourage you all to look at optimization methods, right? This is called elbow detection. Elbow detection, right? And it is how we were able to pick the correct polynomials, and it was also how we were able to avoid bias in the choices for that, right? So when the model runs for us, we don't have any parameters. We let calculus handle it, right? So we look at the errors over time, we find the sweet spots of points of diminishing return, we choose it, and we go forward. The same thing happens in unsupervised learning, right? The way cars decide whether to turn left or right is based on expected value, and it will happen when expected value has the best chance of getting you through versus not, right? So, okay, so that is like the secret sauce behind this. Before we jump to data mining, I'll just talk about where things are not going well, okay? Because I think everybody has seen, yes, nationally things are looking better, but there are plenty of places, and this is actually alarming. I looked at this this morning. By the way, from Module 1, you may remember that one of the biggest challenges we have is dealing with big data. That is entirely still the case, right? And this model takes 8 hours to run, and it cannot run with conventional techniques. There's no way to get all this data into RAM, right? It's just not possible. I don't have 128 gig of RAM to run on my laptop. And so you end up using things like Spark and Hadoop because they allow you to compute in memory, and when you run out of memory, it will page to disk for you. So long as you have disk space or access to other machines that have disk space at a worst case, you will still be able to make the calculation, right? So, okay, so that's there, right? So, and this is current as of 10 o'clock this morning. I ran it overnight. Luckily, it finished in time for the presentation. Okay, so what you're looking at now are the top 10 places where deaths are taking off as far as one version of anomaly detection. What we do is we look at, we have this is death rate, but let me show you deaths proper, right? So we have this best fit line chosen from using calculus to find the point of diminishing returns, okay? And so you can see here it was stepping up fairly linearly, right? And this is Appomattox, Virginia. Okay, and so up until 2, 4, 6, 8, 10, roughly 2 weeks ago, and there's a turning point here. Same thing. We look at the curve and we try to find maxima and minima, right? Again, using calculus, right? And you can see that they've gone from roughly 9 to 23 people, and this is small, but it's a big percentage jump, right? And what's alarming about this, I don't only have so much time with you folks, so I'll go faster, is number one is this jump in Appomattox, Virginia. So they've doubled in the last 2 weeks, okay? And this is death now, right? We're not even talking infection, we're talking death only. And then, because infections, it depends on who's getting infected, right? So I've always been more concerned with deaths and death rate. What is alarming about this is I think the top 5 or 6 are all in Virginia right now. So if you happen to be in Virginia, I don't know what is going on, but something is happening in Virginia. And so Louisa, Virginia is the next one. And so here you can see very clearly, right? They were, again, small number 14, but now it's jumped up to 26. So it's doubled, right? And it starts like this, right? So they're small numbers, and since they pick up exponentially, it'll compound and run. All right, so number 2 is Louisa, Virginia. Number 3 is Amherst, Virginia. Okay, so again, in the last 2 weeks, they were at 14, and now they're up to 35, right? So again, steady, 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 big jump. And then we have Albermay, Virginia. Okay, again, big spike, right? And so I think this is the top 4 or 5 now. And then if we keep going, Chesapeake, Virginia. And I know you're thinking I'm only looking at Virginia, but I promise you I'm not. You will see a data point that's not Virginia in a second. So again, Chesapeake, Virginia, this is a little bit more people. So before the big spike, you were at around 150. Now you're at 241. So 50% increase, right? 150 to 275, yeah, about more than that, right? And so nearly double, 75, let's say, 75% increase in 2 weeks. And suddenly, right? Definitely not a logistic curve here as well, right? This is on the move. And then I don't know where Dinwiddie, Virginia is, but again, another Virginia point. All right, again, 20 to now roughly 40, okay, in the last 2 weeks. And then I'll just keep going until we get Campbell, Virginia. I will keep going until we don't see a Virginia point. 30 to 80 in the last 2 weeks. This is skyrocketing. No sign of a slowdown here, right? And Martinsville, Virginia. Okay. Again, this is on the move, right? So roughly 40 to now 70 in the last 2 weeks. And then Petersburg, Virginia. This is astonishing. So Virginia has really exploded. I'm not even going to look at this. I just want to, okay, good. And so in the same screen, this is not Virginia. This is, I want to say Levi, Florida. Okay. And so Levi, Florida went from roughly 25 to 45 in the span of 2 weeks, right? And so this is a big digression from what the trend was. So there are definitely hotspots, and something is going on in Virginia. Does anybody know? Has anybody seen or heard anything? But I can promise you that Virginia is on the move. Okay, parts of Virginia are on the move. And so, yeah, this is just, I mean, I don't know. Yeah. Yeah, that's possible. And then, thanks, Stephanie. And then the other possibility is Maryland and Virginia are 2 places where people have been sent back to work on site. This is this is ridiculous. So, I mean, and the reason for that is the federal government is here. And so, and there's some places where the work cannot be done. Okay, this is a great question, John. So I publish, and this came up this morning for me, right? I hadn't looked at Virginia in some time, but I'll share it out with them because I think they do need to know. It is definitely on the move, and it is hard to get through to them. I can tell you I knew in March, right? Like, I knew very quickly it was exponential. I knew China was not lying about the infections, and so we don't know about deaths, but they did talk about it, and I trusted the World Health Organization, right? So I knew there was going to be chaos, and I can tell you that I reached out to CNN, I reached out to Fox, I reached out to the White House. Nobody wanted to hear it. Nobody wanted to hear it. Could have been the administration. I don't know. I continue to publish. You can look and get data, and you'll see back, in March, I said we need to lock down. I am of the opinion, actually, that at least in spots like this, where we know it's taking off, that there should be local lockdowns or enforcement. Because, one thing is the people there are at risk, but the second problem is that this is how variants come about. And there are variants everywhere. This thing mutates every time it jumps, right? So it's just, is that mutation prevalent enough and in enough people to be recognized? And we already know that it's on the move and we're having problems with efficacy. Okay, so we're running short on time here. Let me see if I can give you some good news. And then I don't know if we have time to get into the data mining side of things, but let's see. So we have screens for all of this stuff. But let's say we should be able to say least deaths percent death infected. Deaths peaked. So these are the places where we think that deaths have, peaked and stopped. So let me pull this up. This is the death rate for unassigned. This is unassigned, so this is a little spurious. Let me see if I can get you a city so it makes a little more sense. Unassigned Alaska. So unassigned is interesting. If you look through, a lot of our data comes from Hopkins, and I encourage you all to look at that. It's from JHU. You can go to their COVID tracker, and they give you a link straight to it. But unassigned are people that have died within a state, but they don't know, they're not attributing to the state. Perhaps they're from somewhere else. They have no documentation, or somehow they died and nobody knows where they live. It could be homeless. And so here's an example. So unassigned in Alaska, this is infected, but let's look at deaths. There are no deaths here. Please also use the survey link, yeah. And so let's see if I can give you a better example. Is, again, out of Colorado. See if I can get you a city here. Most of these are, Let's do infected, yeah. Okay, so here's a situation where the unassigned in Utah, and I never thought I would see this, but you see this in data science everywhere, but I'm surprised we see it in COVID. There are instances where people have passed away and we don't know where they are, and they've been at least counted, but they've been counted as unassigned. And so there's an infected for Utah, right, where there was nothing for the longest, and then it took off. And what we're saying here is that this looks like infections are peaking, right? So hard to see it for deaths because all of these are unassigned. And when you have small data points, it's a little bit easier to be whipped around. But this is good. Let's look at Washington, Utah. Again, there's too few points here. Okay, all right. So we close with this because we're running out of time. Nationally, it looks like infections are dropping. Deaths look like infections are dropping. I believe they're dropping largely because of the weather. As people get together, the vaccination rate is not fast enough, so please be careful. What else can I give you? Yes, okay, any questions? John, if you have time, I can take them through the data mining, but if not, we can wrap up here.
Yeah, we have time. If the audience will stay longer, yeah, that is fine with me.
Okay, yeah. So it should. I'll go quickly, but I wanted you to.
And those of you who have conflicts with time, if you need to leave, yeah, feel free to leave. But make sure you sign in, and then also do the survey before you leave. But yeah, we can stay another, how many minutes more? 10, 15,
I think it'll
20?
be about 10 to 15 minutes tops. So.
Okay, it's all yours, Prem.
Okay, then. Thanks, John. Yeah. Yep, that is a good point. Yeah. Okay, so let's look at a data mining example. Okay, so that is here, here. Okay, so let me start with, I'll start with the problem, right? The death rate in Alaska one more time. Let's pull that up. So I'll do death rate, and infections for you. So that's here. What you saw was unassigned, but I'll do it for the state. So, question from the audience came in for, let's just do Alaska. You can see there's some 21,000 charts in here, and that is because it goes all over the world to do this stuff. So, give it a second, we'll pull Alaska up for you. Okay, as that's going, the University of Maryland Eastern Shore conducted surveys for its due to the weather. Hard to do, but I do think it can be done. So the question was asked, can we predict if it's based on the weather, right? Let me see if I can get the exact. The chat flew by very quickly. Okay, and good, we have Alaska. Can we predict if it's due to weather or vaccination, a percentage of variation due to weather? You can. It's tricky to do. What has to happen is you need another place like us that has had good vaccinations or is vaccinating as well, or is not vaccinating and has had weather phenomena like us, right? So, and then you can compare, right? You can say, okay, look, we're similar, and they did not vaccinate and had similar weather to us, okay? So they did not vaccinate, they had similar weather to us, and let's say that their infections were much higher than ours, right? Now you can say the only difference between them and us is that we're vaccinating, right? And so the association is that the vaccinations are helping us, right? And the more data you have, the easier it is to build a correlation. But we're going to talk, this is actually the data mining side of this. You need to have an example where you could show that one of the variables was not causal, right? So hopefully that makes sense, right? So we need to find another place that has had similar weather to us, so maybe Canada, and is not vaccinating as quickly as us, and then we can say that the vaccinations are, negligible or not. All right. So it's a good experiment. I'll look at that as well. Okay, so Alaska overall, right? So we have a lot of stuff in Alaska, but you had said, let's look at deaths. There were a bunch in here. Okay, while that's going, okay, so the University of Maryland Eastern Shore, I'm at the University of Maryland College Park, but I work with two professors, a professor out there, and they ran a survey of their graduating seniors to say, how do you feel about what you've learned at the University of Maryland, and what are the key factors, right? And so this is a shot of that spreadsheet that came out, right? And so they have all these variables, right? And I wanted to show this to you guys, and it'll be quick, but I wanted you to see how we can go through and data mine very quickly, right? So a survey is done, okay? And, they ask these questions. Are my academic needs met through classroom instruction, real-world application, et cetera, on campus? And each of these questions can be rated 1 through 5, 5 being the best, 1 being the worst, okay? So here's the question, here's a synopsis of what it is. And here is the variable name that we have in code, because otherwise the decision trees and association rules would explode. Okay, so we ask if their academic needs were met, if their social needs were met, if you felt like you were a member in the community, if you feel like you're in the information loop, right? So a whole bunch of things do you have. You know, do you experience high school pride? So there are all these factors. And we wanted to see what were the associations before we went fishing. Okay, so this is a point that was made back in Module 1. Before we say, let's run this thing through a decision tree and get classifiers and say what the dependent variables are, maybe we want to just see what's happening, right? And so what you can do is once you get some data like this, okay, you can run it through association rules. And that's what we've done. And what association rules will do is find all the implied rules and their confidences and their lists amongst the data set, right? So and you have to think about that. If you were trying to figure out, you know, what do we need to do to improve, let's say, yeah, I think one of the independent variables was I feel more independent, right? And I zoomed out here because I wanted you to see, you know, the amount of questions you have to deal with. If you were trying to crunch this in Excel, there's not that many rows, but there's quite a lot of variables, right? And the question comes up is, if you want to improve something, like you want to improve their academic performance, or you want to improve their feeling of independence or their feeling of responsibility on campus, how do you do that? What are the variables that you target? And where do you spend your resources? Okay, so it's a daunting problem, and it's done kind of empirically by maybe filtering on columns to say, well, when this was good, but the amount of combinations that you'd have to go through are beyond human reach, right? So association rules do just that, right? They look at, okay, you know, this was a 5, this was a 5, and this was a 5. And maybe when these 3 things were 5s, this was a 5. And maybe when these 3 things were 4s, all the combinations, right? You and I may care about what it was when it was, top scores, but what if it's not top score? So it goes through all the combinations of these variables and finds the co-occurrences, okay? Like brute force, there are some trimming methods we use to do this, but for the most part, it computes all combinations, okay? So what does that look like, right? This data set, when run through association rules, and I'll jump straight down to, what the results were. But, here's that data set, right? So these are the abbreviations, okay? And again, we've not set, what we want. There's some labels that are set for a decision tree. Actually, let's go further because we do the decision tree first, but the association rules part is independent of this. And so, okay, so that data set, okay, I've just taken the first 5 rows, right? All right, and then we encode each of the variables to be text and has an identifier. And what happens is, you'll see this as you go through data science and working with models, you end up doing this thing called one-hot encoding. Pandas calls it get dummies, right? But it basically takes every variable, every data point you have, and it turns it into a column, right? So you can see here, Academy 2 turned into a column. And so now this row has a 1 in it because this one had the academic need score of 2. And this mapping continues on for each combination, right? For each row's value, right? And so this turns into, some massive data frame now, okay? Because we've one-hot encoded everything, all right? And for once you get that, right, then you can find the frequent items. And so this just finds you, okay, these variables happened most of the time. So you get the amount of occurrences of everything. Oh, yeah, my email address, yeah. So if you ever want to reach me, you can get me at frame@umd.edu. Okay, so you get the frequent item sets, and from there, you can derive the rules. Just as we talked about, it looks at every combination and it racks and stacks them based on how often it's happened and then how sure it is, okay? So from that Excel file, you know, I don't think it's possible for humans. Maybe some of you are super geniuses who can do this stuff, but I can surely not do this stuff. But it derived all these combinations. And what it's saying is when you have independence equal to 5 and self-eval equal to 5, the projection is 5 and extra credit is 5. And it gives you the support levels for that. So this happens 26% of the time, right? These combinations exist in 26% of the data set. The consequent combination, this proj 5 and extra 5, exists about 30% of the data set. They take the underlying support as the antecedent. This is the if and then, if you will, right? And then its confidence is 100%. So what it's saying is when this is the case, independence is 5 and self-equal equals 5, this is the case every time, right? And it gives you this for all the possibilities within the data set, right? Now, some things are more causal than others. Causality here is defined by the lift score, okay? So when the lift is higher, right, we can get more into this, but basically there's a way to say that when these two things are together, they're more likely, right? So, if the support levels are higher, then we can say that they're more likely to be causal. So here we can say that, you know, independence and self-eval, proj and extra, I just want to see what those things actually map to. So proj and extra, zoom here for a second. I'm going to control for it. Proj, project work. So I worked in a project that allows me to apply what I'm learning in the classroom. And extra. I'm active in, yeah, okay, there's the variable. I'm active in campus organizations and extracurricular activities. Okay, so we find these associations, okay? And we've not decided what we want to target, but we know that these things are happening, right? So, and they're happening at high confidence and high causality, okay? And you can see that things drop off. So what ends up happening is you do this first, right? This is the sweep, right? What is actually happening in the organization? What is actually happening in the data, right? We've not said anything about what we want to target. We just want to know what are all the combinations of things happening together. Okay, so you can do that. That gives you this. And then you can say, all right, what are the things that we see what the rules and the associations are. What are the things that we want to target, right? Maybe you thought you wanted to target independence and say positive mentoring, or maybe you want to target this extra credit and, you know, personal responsibility and projection. So then the organization decides, okay, we want to target such and such variables, all right, after seeing what the rules are, after seeing what the associations are. And then when you do that, okay, you can run it through the decision tree, okay, and you will be able to, you know, get what the rules are to get certain outputs. Now, before we go there, I always like to visualize things. And so, you know, here you can see that this combination of rules is associated with this combination of rules, or these combinations of variables. But you can actually visualize these things, right? So if you visualize just these rows up here that we have, these combination of rules, that turns into this, okay? And I know you can't even see on the whole screen, but this is basically showing how each of these things link together. Now, of course, this is unintelligible, but the point is we can get at it, right? We know that rule 29, as encoded by this algorithm, whatever that happens, the 29th variable, is related to some other rules, and we can trace these lines to do that. Another thing that you can do is pick a specific rule, right, and show how it draws out in time. So let me go to the bottom of it, right? So here you have a particular, these variables, right? So Proj 5, career experience 5, right? Independent 5, self-eval 5, extra 5. These are all related to each other, right? These things all share this as a rule. And as you add more variables and you say, okay, well, what else is this related to, right? These are, we would call these first hops, right? So these things are very, very closely related, okay? As you add the next hop, right? So this is that same link analysis, if you will. As you scroll up, so this R0, okay, is going to add the next hop of things that are, associated. So we see Proj 5 out here as well. And so there's ways to visualize these things if you need to, right? I think it's very interesting to show how things actually are working together. Okay, so finally, you're in the organization and you say, all right, we want to make some changes. What do we do? Well, as we discussed before, you can create a decision tree, right? And the decision tree will tell you what values of the data in your survey or in your data to begin with lead to certain outcomes, right? So what you're looking at here, and this is the end, okay? What you're looking at here is a multivariable decision tree. Usually decision trees are created with a single dependent variable. We care about productivity. We care about, do you feel independent? Do you feel like your academic needs are met? But it turns out you can actually do these things with multiple variables because, and this is another thing, in the real world, it's never just X equals Y or, Y is a function of X. It's never that way. There's always a whole bunch of Ys and a whole bunch of X's that are going on. We simplify things, but it's multi-variable on the way in and it is multivariable on the way out, right? So if you want to make decisions, because say you maximize this, well, you're going to be maybe affecting another variable. So if you want to find out how to target multiple variables, you can. This analysis, by the way, is beyond the ability of humans, right? Because you're talking about trying to maximize 3 variables. Do you feel more independent? Do you feel like you have personal responsibility towards the university? And do you feel like you have more academic experience? So how do you find the paths and the most important predictors for all those combinations? It's daunting, right? Like it's beyond human comprehension. So I'll spare you all the paths, but it turns out that the best node, right, and you can get this from the decision tree, is out here. So what happens is each of these nodes has 3 arrays in it, right? So you can see the value 00011, 00110, 00011, okay? And what this is telling you is if you were to traverse the tree this way, I'll walk you through it and then we'll conclude. But if you were to traverse the tree this way, you would end up with 11 samples where you had academic experience being 5. You would end up with 11 samples where your personal responsibility was 5, okay? And you would end up with 11 samples where your feeling of independence was 5, which is by far the highest scoring, most positive outcome of all of these, right? You can get that from the decision tree as well. So I'll walk it now for you, okay? So if your career, and true is always to the left, false is always to the right, right? That's how these things work. So just by saying, here's my data, and here are the variables that I want to target. That's it. You went through the association rules. You saw what was happening, okay? You said, we care about these 3 things, right? Show me how this stuff actually breaks out. So the decision tree is saying the best predictor of those 3 variables is whether or not you feel you have career experience. And if your career experience is 5 or more, so 4.5 and lower is this way. Let's say you have high career experience, we go to the right, okay? And if you use your Hawk card is the on-campus credit card to buy things, right? I would have never thought that this was a key indicator, but it turns out it is. So if you use your Hawk card a lot, so less than 2.5 is not so much, but if you use it a lot, we go to the right, okay? If your academic development is high, greater than 3, right, we go to the right. If you feel like you have been listened to, and this is the big differentiator, right? So if you get down here, there are 12 samples, right? And there's about 40 in this decision tree here. We've done that to keep things intelligible, but there's 12 samples here. If you feel like you're not listened to, then everybody goes to low scores, right? But if you feel like you've been listened to, then they score the highest. So from looking at that data set, which you may have paid analysts months and hundreds of thousands of dollars to look at, you could very quickly get down to the key indicators for what we need to do to improve these variables are make sure they have career experience, make sure they somehow spend money on their hot card, okay? Make sure that their academic development is strong and they're listened to, right? Another thing that matters is they don't care about if the professor cares about them. They don't care about if they feel respected, right? They don't care about IT needs. These are the things that you have to target in order to maximize these variables. Okay. And that is how we can do data mining as promised. Sorry for running long. Any questions? Yeah.
Yeah, anyone has any questions for Professor Saga? Okay, I have one, Prem.
Yeah.
Obviously, I don't think, or probably let me say, I don't know if COVID-19 death counting is uniform across the world. For example, in the US here, if someone has COVID-19 and then they die of car accident, it's counted as COVID-19 death. So how does that impact the presentation across
I love this question.
the world?
I love this question. So the answer is it depends on the state. There was a big shakeup about this in Florida. There was a big shakeup about this in New Jersey and New York. And so what was happening in the so specifically to if they die in a car crash, it depends on if they autopsy, and it depends on the protocols of the state, and that is we at least know to some degree political, right? But what happened early on, right, is, and you can look, I can see if I can see it for New Jersey. And I still have to answer for Alaska, right? So I'll do this while kind of illustrating Alaska. What happened early on was we had deaths that were increasing, and then it kind of was flat, and then it very quickly jumped, right? I don't know if you all remember this, but there was a time where they were like, oh, people were dying, but we didn't know they had COVID-19. We didn't have the tests in place, right? And so this comes back to that question about can we prove if it was weather or vaccination? So what happened is they said, hold on, we can't just say it's not COVID because we've never had these many deaths. You know, we were having to make on-the-go morgues. We ran out of funeral space, right? So there was pressure put on the states, and there was analysis there to say these had to be COVID deaths because it took off, right? So there were accounting issues in the beginning, and I think even now in Florida there's some sketchiness in accounting. So, and the way that affects the presentation, I'll jump to it, but you'll see it as a big leap in the data, right? So all of a sudden, if it's suppressed, what you'll see is that things will look normal or as they want it to look, right? It may start to look flat. But when you see big jumps, right, that is either a true indication of an anomaly, an anomalous event or change, or there was a data issue, right? So real fast for Alaska, Alaska's got 305 deaths, right? We're forecasting 368. And it looks like it's slowing down. There's a geometric point here to show that things are somewhat tapering, right? Yeah, so this is for Alaska. And then the death rate in Alaska, let me fetch that. And then I'll look at New Jersey to illustrate John's point. So I think it's death rate. We do it as death underscore rate. We'll just take a second. Any other questions as this is going?
Yes, I have a question.
Go ahead. Yeah.
Yeah. So mine is general. So let's say you have data, right? And what kind of decisions do you have to make to know which module to use in terms of whether you're going with the polynomial or you're doing the first or second derivative? I mean, what kind of decisions and what is the bias towards each module? So I mean, I know it's a big question, but it'll go a long way to know how to approach the data. And what they used here in the US, and everybody was kind of what was like flattening the curve, which people got to know what was that and what model they use, because they don't really show us what they use. They just came and show us a chart and just go with the chart. So what goes into how to predict a module or to choose a module?
Yeah, so this is a great question, right? And this was the central question we had when this model was built, right? How do you decide when you're going to flatten a curve? How do you decide what variables to use and what techniques to use? Okay, so our stand is that you should always use math. Okay, and you should always try to use, in our opinion, calculus-based models. Okay, particularly for time series, right? I think it's the most understood, and it gives you the ability to see the equations. It's that much more supportable, right? You can predict very easily, and then you can take derivatives. Now, as soon as you have equations, and it's particularly if they're polynomials, we know they're differentiable, so you can get the derivatives. And if you get the derivatives, you can figure out where is it going to be maxima or minima, right? So that is always the recommendation. Now, Python has a whole bunch of modules to do this, right? So NumPy can help you, right? There's a stat package, a statd, that you can use. There's also sklearn, which you can also use, right? They have different implementations, but they come to the same thing. NumPy is a little bit slicker in that NumPy will actually solve where the derivative is equal to 0 and the second derivative is equal to 0 for you, right? So there's a way for them to take an equation and say, okay, here are the points that are going to be critical in our inflection points, right? Now, there is a caveat, right? And if your data, okay, let's say this is your chart here, and if your data is like, wild, all right, this is not going to fit any kind of polynomial well. It may be too crazy, okay? In that situation, what's happening is we're going to neural networks. Now, because it could be that maybe this is some type of seasonal phenomena that you don't know about, right? And what neural networks do is they're able to project, and there's a formula underneath that you would have to derive it from the weights of the nodes, okay? But they're able to draw these inferences and come up with, predictions that are much more expressive than polynomials, but at a cost, Nana, right? You will be able to get this, and it will find things like you'll see weird functions like this that a neural network can figure out, right? That is not a polynomial. It's not differentiable, right? Part of this whole thing works because if you have phenomena that is relatively smooth, you can differentiate. If you can differentiate, you can use calculus. So you use a calculus-based network at that point, right? But if your data is truly wacky, right, it's not smooth, it's not differentiable, you've got to find something else, okay? And in that situation, you go to neural networks. And the upside is you will be able to get pretty accurate responses, and that is why for a lot of things, neural networks are being used, because maybe, right now it looks jagged, but there could be some other variables we need to make it more smooth. Maybe our view of it is incomplete, so it looks weird. And that's quite possible. You may not have all the variables, and you may be looking at it wrong. So it appears jagged, so neural networks do well. The cost is that you will not know what the function is, largely because there may not be a function, right? So that is the short of it, right? If you are differentiable, if the data is relatively smooth, calculus-based, use regular regression techniques, right? and then solve for maxima and minima points for where you need to project, right? Where this is going to end, where the bottoms are, where a turning point. If it is not smooth, then you have to move to something like neural networks. Yeah. Yeah. Okay, there was something else, I think.
Yes, so
The
the other thing, I have another question. The example that you showed that has multiple variables, where you said it was not f of x, but has a lot of variables. Can you drop that file in the GitHub together with the Python file you showed, so we can the students can at least look at the data and then apply it to the code.
Yeah. Absolutely, yeah. I'm happy to do that. I'll share it out in the GitHub. No problem. Yeah.
Thank you.
Yeah, you're welcome. And so the death rate in Alaska right now, that was the question. And so currently the death rate, this is in percentages, right? So it's actually, it's not in percentages. So we have to use this 0.0, so 0.5, right? So it is low, right? And it is seemingly plateauing here, but we're forecasting the death rate in Alaska. The forecast is that it drops, seems to be hovering, right? But so much of this is also how many people are there and the density, right? Places that are more dense tend to be worse, except somehow India. I don't understand it. It may be an accounting problem. Maybe they're not counting it properly, but India appears to be beating it, right? Let's look at.
I had a question.
Go ahead.
Hi, it's Helena Thompson.
Hi.
I know it has not occurred yet. However, I am in Miami, and they're predicting, because of the spring break, how COVID may increase, of course. How do they go about, and would that be considered a seasonal phenomenon, or the anticipation? How are they figuring this out in terms of what the different forecasts that you were showing us earlier? So,
yeah,
I'm just curious.
Yeah. So, no, this is a great question. We'd have to look specifically at what they've done, but I can tell you there are 3 or 4 basic attacks. Right. First is you look at seasonal regression, seasonal curves to say, okay, we've had this many people before in here, and then when we have this many people, we've had maybe this much illness, and we're going to say that it's going to happen again. Right. Another way to look, so that's the first one. The other way you can do it is you can look at what happens in other places that have had gatherings as of recent, right? And say, we figure there's going to be this much more infections based on what we saw before. So there's that, and then the other thing is if you take all those out, right, and you don't use prior seasonality or another place where people have come together, you can also spot it by upticks in what's happening there currently, right? So let's look at Miami real quick, and then I think that'll make it a little bit easier. And I'm curious now as to what's going to happen in Miami. You piqued my interest, but very quickly on deaths in India, I don't know how this has happened. I'm still kind of suspicious of the data. I can tell you that people I know in India are getting vaccinated who are like in their 50s. So they're using AstraZeneca, which I think is more readily available, and it's not been cleared here in the U.S. But India's turning point is a couple of months ago. They have, we forecasted 190,000 deaths by the next 2 weeks. They're currently at 158,000. And so, and it looks like they had a chance to eradicate it, right? They had a chance to stop it. And you can see this curve is starting to flatten out. And mathematically, that means there's no acceleration, and they're getting close to the velocity being 0. Right? So they're currently still losing 500 some odd people a day, but it's tapering off. And now let's look at Miami. Infections, or let's just do Miami. I think that should come up clean.
They are doing the vaccinations here in Miami. However, that has not been an issue at all. They've even extended to people who are 55 and younger, who have a pre-existing condition. So it is working in that behalf, but who knows when spring break hits.
Yeah, and I mean, the CDC has come out and said that when people gather, it's going to be that, and it's interesting. The other problem is we knew it was in the beginning. We knew it was lethal, but we didn't know how lethal it was by demographic, right? We didn't know that certain age groups were doing much, much better than others, right? And so now we know that. I think the youth knows that. And so the youth is kind of convinced we're going to be fine, right? And so they go out and, they're going to, be close to each other. And, but it is people who have comorbidities. CDC says 2.5 comorbidities or higher, but technically if you have 2 to 3 comorbidities, you're at serious risk, right? So, and maybe that's the shop owner or their poor professor, right? So, these are the folks that get hit. And the other thing that is not being thought about is if you let them come together and the infections rise, okay, fine, maybe they all walk away and nobody gets hurt because they're young, but you have let the virus learn, right? And ta-da, we may get a new variant right out of that, right? So, yeah, I'm very much against having that right now, and at least masks, are helpful. Okay, so there's Miami-Dade. Is there a place in Miami that's specific, or do you just want to see Miami in general? Ohio.
Miami-Dade, more or less Miami Beach, because that's where everybody gathers mostly.
Yeah, so we have Dade. Yeah, so I only have Miami-Dade for Florida. Okay, so let's look at this. So let's go to deaths. The larger projection. This is Miami-Dade right now. So in the beginning, it's picked up, turned, then it slowed down, and now it's turning. It looks to be turning again. There are 5,619 deaths. There'll be 5,800 deaths in 2 weeks. It appears to be linear, and it's possible that it's cubic, right? It's possible that it could start to turn, but it doesn't look like it, right? As you remember from diminishing returns, when we ran it on this data, the point which is most accurate and least likely to overfit is this linear curve, this line here. And so we think it's going up. So I show this to you because as the data changes, you'll get upticks, and if that uptick is strong enough, then you can, pick up and say that it's going to increase, or make the projection that it's going to increase. But the CDC, and I believe most folks are saying, if you get together, there's going to be infections. Still the case, yeah. And so, yeah. Any other questions? Yeah, you're welcome. You're welcome. Yeah. Mm-hmm. Yeah. I prefer to look at, these are the things, the associations that come out of this, right? So what I do is I look at this and say, all right, it's increased or it's changed, and then I think about why. And that's why I was like, what has happened recently that's caused the infections and deaths to drop nationally, right? In particular, Texas. Texas is just, very interesting to me. So what has happened recently that caused the change? And I see it as weather. And I think that it's looked at the same way. For the Christmas holidays, people got together. We had a spike in infections. For July 4th, that was there. We had a spike in infections. The protest led to some spike in infections and deaths. So deaths in Texas. And okay, so Texas is on the move, right? So Texas has lost 45,000 people, and here, so it starts off pretty gradual, takes off, starts to plateau a little bit, takes off again. Some signs of plateauing, but best fit for us is this line here. right? So 126 people per day. But the thing is, we are forecasting 40,000, and Texas is already at 45,000. So this is a digression, right? Most recently from the best fitting line. And that happens because this line factors in all these points, right? So we have a digression here, and at some point, the line will, we'll have to adjust the model to say, okay, no, it is much closer to actually the possible, which is this yellow shaded line, yellow dash line. And so, yeah, I don't understand. I know that there's been a drop in infections. Is anybody from Texas in the room? Yeah. So I would not look at this and say, yeah, let's release all factors to prevent it, right? Like I think it's very risky what they've done. I remember looking at the infected numbers, and that showed some signs of drop. Just look at that really fast. Any other questions as we go? Let's look at this. Okay, so Texas.
Okay, so if there are no other questions, again, thank you all for coming, and thank you, Professor Saga, for an insightful presentation. And Professor Saga will come back again in, I believe, for Module 6. So
Yeah.
we are not done with him. We will see him again in a couple of weeks. And then, so next week we have Module 4, which will be cluster analysis. So the usual time, Thursday and Friday, 11 to 1:30 p.m. Eastern Standard Time. So we'll see you again next week, and then have a great rest of the week.
Hi, everybody. If you need me, send me an email. You can always reach out to me. I'm happy to answer any questions. Stay safe. Wear masks. I wish everybody the best. Yeah. Yeah.
And also, I just saw that there is the TA sessions. So look out for that. If you have any to discuss anything, is this afternoon and tomorrow. No, this afternoon, 4 to 5, Saturday, 9 a.m. to 10, and Sunday, 5 to 6 p.m. Those of you who want to take advantage of that. So again, have a great day, and then see you all in a week's time. Bye-bye.
Bye, everybody.
Yeah, thank you. Bye.